Hello, everyone. Sorry for the little delay, but welcome back to Advanced Track Part 3, where today we're going to be talking about modern CNN architectures. If some of you were here last time we talked about kind of the basic underpinnings of what makes a CNN and how CNNs work. And so today we're going to be basically talking about how nowadays people have been building convolutional neural networks, specifically for image classification, though we'll touch on a few more applications of how people are using this now. Again, here are this is the asset cluster, so you will be able to access the slides if you want. The link tree, which contains link to our Discord, has all the announcements and stuff like that. Every time I post new recordings, I'll notify you there as well. And this time we finally have a feedback form, thanks to Oscar. So that's something we also have there. You don't have to open it now. We'll also put it at the very end. So before we begin, any questions? Kind of just like if you don't remember much from last time, what is a convolutional neural network? Things like that. What is computer vision? Okay, cool. Let's begin. So today we're going to be talking about the following things. We're going to be talking about some regularization techniques, which is the concept of, has anyone here not heard of the term overfitting? Or can anyone explain to me what overfitting means? Yes.
The model is being too good on classification of the training data, so ultimately it leads to bad score for the actual test data.
That is absolutely correct. The model is basically learning in a way almost too much of a training data, and it's not generalizing to kind of like the overall features. And there's a lot of different reasons why that can happen. For example, if we have a really small training set, or in certain ways of training can lead to overfitting. And regularization is a way for us to combat that. And then we have some basically advanced convolutional neural network architectures, Inception, ResNet, and UNet. We don't have demos today, but then I'm thinking of adding some demos for at least ResNet during our practical code sections, which will be week 5, 6, and 7. A little bit of pre-training, a little bit of transfer training. And for those who want to stay to learn, to hear a little bit more about this, I also at the end have a little segment that talks about Python, why we use Python, what is package management in Python, and why we sometimes may refer to things called virtual environments, and also by extension, why Google Colab is so convenient. So yeah, let's begin. So let's talk a very short history of convolutional neural networks. Okay, so you want to begin?
Yeah. So because today we'll be talking about like more advanced convolutional neural networks. So we have to understand like the classics first. So one of the earliest convolutional network is the Net 5. It developed in 1998. It was developed to do a classification task between handwritten documents and also machine type documents. And it's called LeNet 5 because it has 5 trainable layers, which consists of 3 convolutional networks and 2 fully connected networks. And then between the convolutional networks, they apply average pooling to condense the features before passing it to the next layer.
Yeah. And fun fact, the reason why it's called LeNet is because it is proposed by the, I talked about this a little bit last time, but then it's proposed by the NYU professor Young LeCun. And it is kind of like the first really widespread use of convolutional neural networks or convolutional layers because it was, I believe he collaborated with the USPS or the UPS to do handwritten digit and letter recognition to basically do something called optical character recognition, which is you take a picture of the mail label and it just converts it to digital text for you, which you can imagine how that would be very helpful at that time.
And then the next one is AlexNet, developed in 2012, and it's kind of a revolutionary architecture because, well, we'll talk about this more later, but what you need to know now, it's because it has like deeper and more filters in the convolutional layers, and also features the ReLU activation function, which is as opposed to like 10H or sigmoid functions that is like previously more popular. And then it also, during its training phase, it's also utilized multiple GPUs, which significantly increases the training speed.
So also, if you look at the years, you can see that there's like a significant gap between these two like years. So like 2012, like around then was like machine learning and neural networks coming back again into popularity due to like better GPUs and better like hardware. So that's also something that's
yes. And another thing is, I've heard a lot of kind of machine learning professors talk about this, but in between these two eras is kind of like the winter for deep learning again, because people kept running into gradient vanishing errors when they were trying to do deep learning. Does anyone remember why that was a problem or what that problem is? The next slide. Let's go.
you could go for it.
Was it because the derivative, like the classic sigmoid function, it scales smaller and smaller as you take the derivative?
That is exactly correct. With both tanh and sigmoid, when you take the derivative, what happens is the derivative itself is actually typically lower than 1. And kind of even more importantly is the fact that because you're kind of mapping this negative infinity to infinity to kind of limit it to some amounts, you're kind of limiting the amount of training that's happening when your output values are really large or really small. And we call that when we're saturating a neuron. That's the term we use. And that created a lot of problems because then your gradient just was really low in general. It's really low in magnitude. And that made deep learning training not very possible, especially when you have a bunch of different networks where you may imagine how this problem can kind of increase exponentially.
And then, so before we dive deeper, this is just like a quick review of convolutional networks. So convolutional networks, of course, like features convolution layers. So in a convolution layer, well, a filter will go through the image and then produce a convolved feature with its own weights and So you can imagine there's multiple different weights with different different filters with different weights, and then at the end of the convolution, there's like a stack of multiple different convolved features, and then that will be passed on to a pooling layer, which is a technique to condense our feature while preserving the most important information. And then there's like two types of pooling techniques, which one is max pooling, which is just basically take the maximum of the largest number in a section and then put it over here. And then the next section, the biggest number over here and put it there, and then repeat for every section. And then average pooling is just compute the average of a single section. And then that will become our condensed feature.
And if you remember from last time, we also talked about how you don't have to use max pooling to reduce the size of the feature of the final output feature map of the convolution. You can also use something called stride, which is instead of just moving 1 pixel every time, you're moving the filters, say 2 pixels every time. And you may imagine how if we move the filters 2 pixels every time, we're actually kind of almost having the feature map from the inputs. So that's also a way we can do reduction, and both have its strengths and benefits. For example, if you're doing stride, it's less number of operations, and you're almost like having like a learned sort of downsampling situation. But with max pooling, there's some theoretical papers that's arguing that the fact that this is invariant, it has some invariant properties that theoretical machine learning scientists like. So sometimes people do use this as well.
And then the ReLU activation is also really common in convolutional networks because compared to like sigmoid and tanh, if you look at this, the derivative of this function is much sharper compared to like the other functions, which is, I believe it just looks like this. And then it's only sensitive around like 0. But if you look at ReLU functions, like after 0, it's like the derivative is 1. So it will prevent the diminishing gradient problem.
Yes. And also, it's just much easier to calculate. All you have to say is, well, was this feature, like if you're talking about calculating a gradient, you just have to say, oh, well, was this before negative? If it was negative, it's 0. If it's positive, it's 1. So it's a really, really quick operation where you're computing the gradient as well.
And then this dropout regularization technique is also very popular among convolutional networks. So what dropout regularization basically does is it prevents the model from overfitting. So imagine this is just like a regular neural network. So perhaps like if we didn't set any like limits on the neural network, maybe there's like some underlying feature within our training sets. And then our neural networks during the training phase will just rely on this, and this node. And then because like all the testing features have shared these features, they can just like, it's easy for the model to say, okay, so this, and this nodes are the most important ones. But then during the testing phase, maybe the testing data do not have these features. So like our model will perform really poorly. So what dropout regularization does is we basically set like random nodes into 0. So basically just deactivate them, like pretend they're not there. So by doing this, we force our model to actually utilize other nodes and generalize across them, so that when we're doing our testing phase, like the accuracy can be better and not overfitting.
Yeah, and there's also another way of thinking about how dropout kind of works that, why it may help with regularization. One of the techniques that's nowadays classification models use is sometimes they just train like a bunch of models with like slightly different initializations, because if you think about it, we initialize the weights randomly, right? So every time we initialize a different model, it's going to be slightly different. And because of how weird the loss landscape of a neural network is, generally, if you just perform the same steps for training, you will actually get, you actually reach kind of different local minimums. And when you train a bunch of different neural networks, this is called ensemble model. What you can do is actually just say, okay, let each and every single one of them predict, when you're given a test image, predict what this test image is, and just do like a popular vote of like which class it is most likely to belong in. And people have found that consistently you can get like a 2 to 3% increase in accuracy, which is pretty good considering that you're really not doing anything extra besides just waiting for a longer amount of time. Now, dropout is almost like doing that. You can think of it as for every single iteration in which you train the model, you're almost getting a slightly different model because we're randomly zeroing out nodes. So you can almost think of it as like ensembling slash the more precise term is bagging. There's like stuff like that's a little different, but it's almost like ensembling slash bagging, but you're doing it every single iteration. So that's another way that you can think about this. I think that's pretty cool.
Yeah, I have a question. I was just gonna say, is it kind of related to like simulated, I think, annealing in classical searches, where it's like there's like a small chance, I think proportional to like some exponential, of just taking like a really quote unquote bad step in terms of loss in the hopes that you're like escape from some kind of local minimum?
Yeah, that is.
I mean, they both come from like similar theory.
Yeah.
So, yeah. And also, you could think of this as like CNNs versus maybe like fully connected networks. So like usually CNNs perform better on models and like better when images are like more augmented, like shifted or rotated and whatnot, whereas fully connected layers just aren't as good with that. And this is like kind of one of the reasons.
Yeah.
Because there's so many. Like,
and another thing is we don't actually use dropout regularization nowadays on the CNN output layers. Like it's just like, this convolution layer 1 and then layer 2, we don't really put dropout in between. We typically put dropout at the very end in the fully connected last few outputs. If you remember, we kind of do convolution, fun, everything gets one huge long vector, which is like a concatenation of all the feature maps. And then we feed this feature map into like a few fully connected layers. We usually only put dropouts, on those fully connected layers, because if we put dropouts, with fully connected layers, there is this kind of direct intuition of like, oh, we're kind of like zeroing out some of these nodes of the model, right? But if you think about doing dropout with convolution, it doesn't really make that much sense because the outputs of a single like pixel on a feature map is affected by a bunch of different filters, and not just a bunch of different filters, different points of different filters. So it's not the same as just zeroing out some points of the filters. And, that's why we don't really put dropout on CNNs. And also just, honestly, empirically, people have tested it. It just doesn't work as well, but it works well on fully connected layers. Yes?
Is dropping out same thing with freezing the node, or is it different?
Those are two different things. Freezing nodes, that has to do with transfer learning, which I think we either talk about today or next week. But transfer learning is basically, for very, very quick, preview, we take an already trained model, trains at some more general task, then you kind of freeze the previous layers, retrain the last few layers to almost fine tune it for certain more specific tasks. You may have heard of it for like large language models where you can fine tune, let's say, to generate movie quotes of your favorite character or something like that.
On top of that, is transfer learning different thing with continuous learning?
Continuous learning. I'm not.
So you don't learn dog and cat together. You learn dog first, and then you learn cat, and then asking, is it available to learn identify both dog and cat? I think that's what continuous learning is.
Interesting. I'll be completely honest. I haven't really heard of that much. You may be referring to something like contrastive learning.
Contrastive.
I think the name is continuous learning.
Continuous learning.
There's
Okay.
a problem with catastrophical forgetting.
Oh.
Because the learning dog first and learning a cat, it's basically the way how humans learn.
Yeah.
But machines are not really good at that. They're good at learning all together.
Oh.
So I think that's and I think the one potential solution for that catastrophical forgetting problem is freezing the nodes.
Oh, okay. You are talking about something different, but I do like that input because one of the things that people have actually been developing now is let's say we're given like some sort of like DALL-E, like really big generative network or some sort of really big network that's really powerful. You can actually feed it certain training data that basically kind of simulates that catastrophic forgetting and just basically destroys that whole model. So there are ways of doing that.
Sort of like transformers.
Sort of like transformers, but like that is something different and, to be honest, a slightly more advanced concept. I don't think we're going to cover that this workshop, but we can definitely get back to you on how that's related. Yeah. Okay, so I want to talk a little bit about ImageNet and how it all began. So the reason why I talk about this is, if you remember on like a little timeline there, 1998 is when the first convolutional neural network really became viable. But then 2012 is when people really started actually doing research on deep learning again with computer vision. And the reason is ImageNet, right? ImageNet, which stands for BATS, it is basically an annual competition that started in 2010. The idea is very simple. You have 1 million training set images, 50,000 validation set images, and 150,000 test set images, each with 1,000 classes. So if you think about it, it's just a really, really big classification problem. And the competition is just, well, you have a model, you train it. The model will then kind of predict the top 5 most likely classes. If any of those classes hits the ground truth label, aka what the model is supposed to predict, then you count that as a hit. This model has guessed correctly, right? And the reason for doing that is because with 1,000 classes, sometimes you can have multiple elements in an image, and there's some ambiguities. So having top 5 actually, represents the performance of the model a little bit better. So as you can see here, 2010 and 2011, these were both techniques that are not at all related to deep learning. There's no CNNs, nothing. It's just like a bunch of, I talked a little about this last time as well, but it's just like a bunch of techniques of like, they do some, like I believe the 2011 paper, what they did is they took a bunch of, took the input images, took random crops of those images, performed k-means clustering on those random crops, and basically using the center of these clusters to create bags of words, and using those then to almost like convolve on top of the image to create feature vectors, in which then they use some really quick, like very shallow neural network to solve. Like, it's a lot of really complicated methods of shoving a bunch of things together, and it's just honestly not very elegant. And they got 25.8 error at that time, which is like they're guessing 75% of the images correctly, which is pretty good. But AlexNet, which is the first network that uses a bunch of CNN layers, specifically a lot very deep layers, and using deep learning and using backwards propagation and calculating the gradients, and most importantly using ReLU, they have dropped that accuracy by a lot. And as you can see, then ever since then, every year they have been basically absolutely demolishing this task. Human accuracy was 5.1% because I think this was like 2015 or 2016. A bunch of grad students at Stanford, they got bored. So one weekend, they just all sat together in a room and just went through the image set data set themselves, classifying each image. And they realized human performance is about 5.1%. So at 2015, the ResNet, which we will talk about in a sec, actually did better than humans. That is pretty crazy, but just in a few years, you have this really rapid advancement. And then, we'll talk a little bit about history later, but like afterwards, it got so good that people kind of got bored of image classification. Now you have things like generative networks and stuff like that. But it is kind of crazy how literally 10 years ago, people didn't even think deep learning was that viable. Just a little thought. But yeah, now basically this, we can almost say it popularized deep learning, or it was the thing that allowed AlexNet to, become popular in the scientific community, and then people realize, oh, deep learning is viable. So speaking of AlexNet, we talked a little about this last time as well, so I'll kind of just speak through it a little bit more. Basically, it is designed by this dude from the University of Toronto, won the 2012 ImageNet competition, and it basically has this sort of structure, right? You have the initial convolution, do a bit of max pull. Usually they also have right after the convolution, they have the activation layer, which is using ReLU. So convolution, ReLU, max pull, norm. Convolution, max pull, convolution, ReLU, max pull, norm. And you just do 3 convolutions with ReLUs all at once, do another max pulling, and then 3 fully connected layers. Seems relatively straightforward, right? Like they basically just like tested a bunch of different sort of configurations and found that this worked really well. So the question is, why are we talking about network architecture from 10 years ago? And that's because Alex has basically today's default CNN architecture. When we build a CNN with code in workshop 5, 6, and 7, that's basically what we're going to be replicating, but like a much smaller scale because we're working with a smaller data set. But basically this idea of a convolutional network, max pulling, norm, and activation. The order of these have kind of been changed over the years. People have argued, wait, should norm come before max pull? Should it come after max pull? Where should it be? It's changed a little bit, but it's this idea of conv, max pull, norm, activation, or conv with stride, norm, and activation has stayed, right? And and the kind of more overall structure of a bunch of convolutional blocks, some with downsampling, some without downsampling, a fully connected layer, and an output activation. These are, this is kind of like the default CNN architecture today. Like even when I want to build some sort of image recognition thing, that's what I will do, right? And again, you may be building one of these in future workshops. So right before we get into that, I want to kind of reiterate why AlexNet was so important. Is because, again, was the one that kind of not pioneered, but popularized ReLU. Because beforehand, people used Sigmoid and 10H. ReLU basically allowed deep learning to be possible because the gradient vanishing issue wasn't as prevalent anymore, right? You could actually try to tune the hyperparameters in certain ways such that your gradients won't go to 0. Now, you still have the issue of gradients explosion, which is when your gradient gets so big, it basically pushes your model weights to be really big, and then your outputs will become, not a number, and then your loss become very big. Everything's just not a number, and you get really bad issues. There are ways to solve that, and specifically, we kind of hinted at it here, which is normalization. We'll be talking about this in a little bit. AlexNet back in the days, they didn't have that, but it was the pioneer of deep learning, and that's why it is very important. And it's one of the most commonly cited papers.
Okay, yeah. So just going off that, it's called batch normalization, and we'll be talking about it later. Yes. But yeah, so upgrading AlexNet to like a better model, the GoogleNet, and basically we'll be talking about why it was novel because of the inception model. So just like a quick overview of what the inception model was, is it was like this thing where you have, so like basically when you train a CNN, you have like many layers deep of training. However, like the inception module allows you to like convolve over like many different layers with different features. And like one of the, right. So this is probably a better representation of what I just said. So these are like different filters, and they go over different layers instead of having to go like deeper into the network. So because they do it on like different layers at the same time, it speeds it up rather than, taking more time. So that's kind of one of the benefits of inception. So another, I guess I'll just go off on the same thing. So why would this actually help? So as I said, like the greater the depth, the more input volume there is. So it's like like greater depth, more volume. But like if there's lower depth and more spread out, like more flattened in a sense, there's more like, I guess, parallelism and more of a way of like the feature dimensions not mattering as much. So like the feature scaling does matter, and that's also why the inception module is very useful.
Another idea to think about this is when you're computing the gradient, which is honestly the most expensive part of training a neural network, because you're kind of doing these in parallel, when you get to that point, you can kind of split up the gradient you're computing, and then you can kind of compute them separately. And because they're not dependent on one another, what you can do is actually parallelize this whole thing. And with GPUs, that becomes really easy. And especially with today's modules, they kind of just do all that for you.
Yeah, so basically what he said is like one of the greatest advantages of inception modeling, and it's also shown here. So I guess the first one would be the one without inception. So you have a 256 depth and you have 256 5x5 kernel, and you can see how many weights you got to generate, which is like more than 1 million. Whereas this is like about half when you have like a lower depth of the UNet.
Yeah.
So
could you clarify what depth and kernel is again?
Right. So a kernel is basically when you have like a filter, but like, you know, a 3D pass over it. Like, yeah.
So this case kernel, it just refers to like, you know, kernel with a 5x5 kernel. It's the filter itself, right? We use the word kernel and filter interchangeably. Mathematically, they're different things, but, you know, like, you know, ML scientists, we like to really destroy terms. But yeah, so in this case, all we're saying is basically counterintuitively, sometimes inserting like an additional layer actually helps to reduce the number of parameters. So instead of doing a 256 to 256 with 5x5 kernel, you can do a 256 with 5x5, 64 1 by 1, back to 256. That bottlenecking actually helps you reduce the number of weights. Does anyone have an idea, a vague intuition of why that may be the case?
So like you probably also heard of this in like with PCA. It's similar to like variational autoencoders where they have like the starting set of weights, but we want to make the set of weights like smaller, but still representative of the like the previous information we passed into the network. So it's similar to that same thing. And I guess like Jordan's probably gonna give you a more mathematical explanation.
So the idea is this, right? If you have a 5x5 kernel, and let's say your input and output channels are both 256. So let's say they're both 256 first, like that. And the reason for that is because if we're going from 256 to 256, both our input and output channels are 256. Then the total number of weights we need is 5 by 5 and 256 by 256, right? So that will be the total number of weights we'll need to define this kernel. And if you recall why this will be the case is because for every single 5x5 kernel, if you imagine an image over here, it will technically be 3D. So like you can imagine this being like, you know, some width times height times, in this case, our depth is 256. For every single one of 256 by 5x5, we basically convolve it. You can imagine this. We basically convolve it like here, like that. We kind of do a pairwise multiplication. So this is 256 by 5x5. This is 256 by 5x5. We basically do a sort of pairwise multiplication. We add them together. It's a multi-dimensional dot product. And we do that for every single, you know, we pass through the whole image, and that will be one of our output filters. And we do this 256 times. So our output feature map is then 256 in the number of output channels. Now, instead of doing that, we do 256 to 64 to 256. Then what happens is suddenly the number of weights we have is halved, right? The number of weights we have is suddenly halved, at least for the not half, quartered actually, from 256 to 64, because we only need an output channel of 64, right? And you may be like, okay, how is this helpful? Well, when we go back from 64 1 by 1 back to 256, the number of weights we'll then need is 256, which are outputs, times our inputs, times 1 by 1. A 5 by 5 kernel has 25 entries. A 1 by 1 kernel only has 1 entry. So this is basically negligible compared to this. And we add these together, we get a much reduced number of weights. But in reality, we have actually made our network deeper. And what machine learning scientists they have found is deeper networks generally are considered as slightly better than shallower networks are really wide, aka every single layer has a lot of weights. So basically, it's actually better to try to reduce the number of weights per layer and just have more layers. And that is why we will be trying to use things like bottlenecks, is because it just helps reducing the number of weights, which means it just saves memory and it saves computational cost. Does that make sense?
Yeah. So
yeah. Again, like the math is you have to really think about what the hell's happening, with the math. But ultimately, the whole bottlenecking procedure, it does have the counterintuitive effect of it's deeper, but it's actually less number of parameters just by kind of how we define convolutions.
Yeah, so another way to think about this is like you have less weights to propagate from one layer to the next layer as you're going further because of the smaller dimension of the previous layer.
Yeah.
So yeah.
And if you think about it, the purpose of why we do this is because if you think about just how features work, the size of a feature can vary from image to image. So rather than trying to figure out, oh, what is the best size for the current convolutional layer, why not just do all of them and just have all of them extract different features, because different features have different sizes. And if you remember how like what we talked about last workshop with what we call neuroreceptive fields, which is how with more and more convolutional layers, because we're downsampling and because each convolutional layer kind of, like a 5 by 5 convolutional layer captures a 5 by 5 area of the input image, the amount of features, i.e. the amount of area in the total image that the convolution layer is looking at, the more subsequent the layer is, the bigger the area of the image it's looking at. So by kind of combining 1 by 1 filters, 3 by 3 filters, and 5 by 5 filters, we're suddenly getting information simultaneously of, in the later layers of looking at the whole image and maybe just parts of the image. But because of that many iterations of layer, it is looking at it in a, very hand-wavy way, a very general way, if that makes any sense. So it basically allows you to extract more features, and with, image classification, that's what we want to do.
So basically in parallel, there's different sizes of filters going through these images, each image. And because of that, you get more different features because of their sizes varying.
Yeah.
So, yeah.
And this kind of gives you an idea of how the inception module works.
Right. So this is just kind of like a meaty diagram to digest, but any questions?
So you can think about, the input here. This in this case, we have a 28 by 28 image. For each of we have this kind of bottleneck layer happening, right? So that helps us reduce the total number of weights. And then, but we also have these other, 1 by 1 convolutions, again, just to help reduce the number of weights. Basically, we end up with 192 channels here, 96 channels here, 64 channels here, and we also do this kind of really tiny little 1 by 1 convolution thing here. And at the very end, we basically take all these 28 by 28 feature maps and we just kind of say, all right, on the channel dimension, let's just concatenate them all together. So suddenly we have just a bunch of feature maps.
And this automatically makes your model a lot more powerful because you have way more features that you're looking at.
Yeah.
So the key is to do things in parallel.
Yeah, because GPUs also operate in parallel, and because you can do things in parallel now, you have the ability to generate a lot more features as well. So there's 2 of them.
So is the purpose of foremost left layer perhaps to capture simpler features or shallower features, whereas the other layers can get following the extrapolation that Jordan mentioned just now, they can kind of pick up on bigger chunks of the image.
Yeah, absolutely.
Basically, so 1 by 1 would be 1 pixel by pixel, more or less. But if you go to 5 by 5 or 3 by 3, per se, it's more of how the pixels together interact. Yeah.
Okay. Yeah. Oh yes.
Just to make sure, so the way that the bottleneck layer compresses the depth, it's because when we use like less number of kernels and every time, so instead of using 256, if we use like 64 kernels, then like it will just produce 64 feature maps.
Yes, that is absolutely correct. It is the idea of like your input and output channels will be multiplied together. So if you reduce one of them, and if you use a smaller kernel there or something like that, then you will actually be able to create deeper layers with actually less number of parameters. And the one by one also just helps to reduce the number of parameters because suddenly we have reduced our number of parameters by 25-fold, right? At least for that layer. So now let's get to sort of the elephant in the room, sort of, the thing we have kind of been building up to, which is ResNet. And if you don't remember, I'm going to come back here to this little history diagram here. We started with AlexNet. For 2013, it was, I think it was like an improvement of the AlexNet-ish architecture. Not a lot of people talk about it. 2014 to 2015, BG was basically like a better version of the AlexNet, and then GoogleNet was what we looked at, right? What happened and what was the architecture that allowed us to get to ResNet, something that finally passed the barrier for, in a way, human cognition, right? And the idea is residual layers of concepts so unbelievably fundamental that almost every single neural network today you see, OpenAI with their DALL-E and ChatGPT, transformers, just every single neural network will try to incorporate residual layers in some way or another. And the idea is, surprisingly, very simple, right? So basically, we have the network learn what is called a residual added to the input instead of a raw transformation. It'd be like, okay, what does that mean? Do we have a diagram? Let's see. I hope we have a diagram. Yes, there we go. All we are doing is we're saying, okay, in addition to passing our inputs through our convolutions, let's make a copy of our inputs and just add it to the outputs. That's it. I'll just let that sink in a little bit. That's all we're doing. All we're saying is just make a copy of our inputs, for one of the copies, actually passes through all the convolutions in our current layer. And for another copy, skip all those layers, add it together. That's all we're doing. And to kind of understand why we're doing this, we kind of have to, motivate it a little bit, right? So the problem was ResNet was trying to solve the issue of going deeper. And the reason is people actually realize that deeper networks have actually, up to that point, deeper networks have achieved better performance. But we run into what is called a degradation problem, where at a certain point, we start to get diminishing returns, where adding more layers, the amount of computational costs are increasing doesn't actually really justify the amount of performance increase. And up to a certain point, it actually starts to do worse, right? So in this case, we kind of have this idea, right? Suppose we take a shallow network and add additional layers to increase its depth. If we train this model, it will perform the same, better, or worse. Yeah, so in theory, this should perform at least as well as a shallow network, right? Because the additional layer can learn weights that make it the identity function. It can just learn weights that basically does absolutely nothing to our input feature vectors. However, in practice, the extra layer seems to have actually trouble learning identity mapping, but a much easier time learning a zero mapping. So to basically kind of say what this means, it's basically when you actually add more layers, what happens is these layers actually learn to basically map your outputs to zeros, which is not a good idea, right? Not a good idea at all. So basically what happens in practice is suddenly your distribution of weights gets closer and closer and closer and closer to zero. And that's not even really a problem with gradient vanishing. It's just, if you do the math, that's what it kind of ends up being, just by how neural networks are designed. And that can be problematic. And the solution they came up with was adding this kind of skip layer, right? And adding it to the output. And the idea is this. When we add the skip layer, the network suddenly becomes both shallow and deep at the same time. Because when we're calculating the gradients, we have gradients that are kind of passing through these weight layers is making it really deep, and sometimes you may decrease the size of subsequent layers, and it actually has diminishing returns. However, by adding the skip layer, what happens is you're actually almost making the network shallower. You're allowing gradients to pass through, and because of that, you're kind of maintaining the magnitude of the later layers.
Right. Also, another way to basically think of it is, so like you have like the degradation problem, and you have the weights zeroing out, right? So if we propagate the weights without like doing anything to it, it's like an identity mapping. So that's like one of the other reasons why residual blocks work really well.
Yeah. And another thing that kind of people have kind of figured out why residual networks work so well is actually has to do with the loss landscape. One of the things with deeper neural networks is, if you remember from workshop 1, I kind of showed the diagram of like, the weights in this axis and another dimension of the weight in this axis, and we have the z-axis as how what the loss is. If you remember, like with more complex networks, you may have a very jagged loss landscape, and that makes optimization, aka pushing the weights around to figure out where's the minimum, a lot more difficult. However, what people have found is residual networks actually helps to smooth it out. Do we have a mathematical explanation of why this happens? Not really. That's one of the really almost weird thing about residual networks is it's used so commonly, but we don't really have a very, very solid mathematical, rigorous explanation of why it works so well, which I think is kind of intriguing. But this idea is almost used like everywhere nowadays, of like basically just like skipping a bunch of layers. You will see later they also have things like DensNet, which just keeps skipping bigger and bigger ones, and you skip to everywhere, stuff like that. As long as you don't create you'll be okay, So that's basically what the residual layer is. And another thing with the residual layers that I actually kind of want to show you, if we go to the paper itself, because the paper was quite legendary. Fun fact, the paper currently is the most cited paper on Google Scholar, period. Is the ResNet, because it was so influential. But if you take a look, one of the things ResNet's managed to do, like you can kind of see it here in its architecture. We have like a bunch of convolutional layers that just skip, right? And if you kind of notice here, when they compared it to previous networks, one thing that ResNet's managed to do is achieve very good accuracy. So this is like a train on 7%, but at a much, much more reduced number of parameters. I believe VGG, which is like a very close second place of the 2014 ImageNet competition, had like 600 million parameters. But with ResNet 50, which is already a model that performs much better than the VGG model, it only has like 25 million parameters. You have much more reduced number of parameters because they employed a lot of different techniques, such as if you see here. If you see here in the way they design the model architecture, with the deeper ones, they use our bottleneck, right? 1 by 1, 3 by 3, 1 by 1, 1 by 1, 3 by 3, 1 by 1, right? They're using the bottleneck feature, and basically they're using actually much smaller number of channels on every single one of the layers, but then they're able to make it much deeper because of that skip connection. Because of that skip connection, they're able to make the network much deeper and also much thinner. So imagine, like maybe the previous networks were really wide. They basically managed to thin it down and just say, let's have a very, very, very deep network. And it's shown that it is able to learn a lot of features of ImageNet. And one last thing, I think pretty notable for ResNets. They're not the first network to train this way, but even if you just try to train it with normal networks, this training method works really, really well for almost any convolutional network. But before we talk about it, we have to talk about batch normalization. Another thing that was proposed in 2015 that ResNets used that made them so good. So batch normalization normalizes the outputs of a layer so you have 0 mean and units or 1 variance. So if you imagine we have like the outputs of a certain convolutional layer, it may be very oddly distributed somewhere else. It basically says, all right, let's take all of them, let's just shift it back to like a nice normal distribution here in the middle. So the way it works is this. if you imagine we have some sort of feature map like this, right? What it's saying is for each entry on the feature map, we normalize them across the batch. So to kind of visualize that, if we have, like, let's say a feature map here, and we have, for each feature map, obviously we actually have a bunch of channels of feature maps, but let's just say we have one feature map. And because when we are training neural networks, we pass in batches of data, 128, 256, something like that. We basically take that one feature map and imagine 128 copies of it because we are passing in 128 different images. We're basically saying, all right, for pixel 1 on the feature map, look at that one pixel across all the 128 batches. We take that as kind of like our statistical data, normalize it. So take every single one of those values, make sure their mean and standard deviation, mean is 0 and their standard deviation is 1. And we do that for every single entry on our output feature maps across every single pixel over every single channel. And that's it, right? And the key of why this really helps is because it helps with gradient explosion. In other words, when the gradient is very big and causes the loss to go to infinity. So let's say we don't have batch norm and we were running into problems with gradient explosion. How would we solve that problem? Let's say we don't know about batch norm. Like how did you think machine learning scientists managed to solve that problem in the past? Remember when we were altering the weights with the gradients, we're subtracting the gradient from the weights, we're multiplying it by something. What is that something called? We use a very small learning rate. Basically, back in the days, what the ML scientists will do is they'll just very carefully tune in learning rates, right? Because the learning rate doesn't have to be constant. You can, make it start small because usually for the first few iterations, the rates are very big. You can make it start small, slowly ramp it up, and then slowly drop it down again. Like they did a bunch of really very, very fine-tuned ways of tuning the learning rates. But basically, batch normalization says you don't need to do that because of this whole normalization process, the gradient is never going to be big, because we're normalizing what the output is, right? So what that allows us to do is a really fun way to train neural networks, which is something called piecewise constant decay. This is actually exactly how the ResNet is trained. We start with a very large learning rate of 0.1. That is huge, by the way. Like normally, if you're talking about later we will learn a little bit more about optimizers, but if we think like gradient descent, we usually start with 0.01, 0.001, right? And then so 0.1 is huge. If you train any network without batch normalization with 0.1 learning rate, that's like any depth, you're going to run into gradient explosion and have all your loss, everything be NAF. And start with 0.1, and you basically drop the learning rate by a factor of 10, so 0.1 to 0.01 to 0.001, when the learning rate, when the learning plateaus. In other words, they have actually kind of hard set this in the ResNet, I believe. They train it for a total of 64,000 iterations. They drop from 0.1 to 0.01 at iteration 3200, and they drop again at iteration 48,000. So 32,000, 48,000 at a halfway point and at the 3/4 point. And you can actually see that happening in a loss training graph. Actually, I think they drop at different points, but the point so stands, they actually drop it at different points. You can see initially the error is very high, right, over here. And then at this point, they realize, oh, learning is plateauing. Let's drop the learning rates. They drop it, and you can see the moment they drop the learning rates, we have a huge boost in performance. And they drop it again, we have another huge boost in performance. So this has shown, using this with stochastic gradients with momentum, if you think about momentum is basically having a moving window of the previous gradients. And that basically allows you to be able to kind of, because of, it literally is like having momentum, because when let's say you have something like this, right? With normal gradient descent, you may descent, like let's say it's your starting point. With normal gradient descent, you may descent here. And because then your gradient becomes 0, it kind of just stops moving and it just oscillates a little bit and you will stop here. But with momentum, because it remembers that in your previous iterations, you have been going in this direction a lot, it will kind of just say, all right, I'll keep pushing you for a little bit and kind of decaying. And that may be enough for you to make it through this value and maybe get to a better local minimum. So that's the idea of momentum, and that's why people use it. With that in mind, why do you think we would potentially, what is the intuition behind potentially using this idea of starting with a really large learning rates, doing a bunch of training on it, and we know we won't with fits, right? And then dropping it again and then dropping it another time. Why do you think that may be helpful? It's not a very straightforward explanation. You need to do a little bit of intuition checking, but
what's the question again?
Oh, the question is, why do we do this sort of dropping? Why does it work so well that we start with a really large learning rate, after a little bit drop it by a factor of 10, and after a little bit drop it by another factor of 10? Why do you think that works, as opposed to just trying to start with a smaller learning rate and make sure we don't just jump around the loss landscape?
If we don't reduce the learning rate, if the error curve looks like this, we'll just like going back and forth forever.
That is correct. That is one of the ideas. And so the way I understand is this, right? If we imagine our loss landscape, we will have something very complex, right? Something with a lot of nooks and crannies, that maybe looks like this. When we use a very large learning rate, because we're jumping around the loss landscape by a relatively large amount, what happens is we do that a bunch of times and kind of sporadically moving around because we're jumping around so much. What happens is the place that we eventually end up in will be kind of like a potential candidate location for a close enough to global minimum, local minimum. Because we've been jumping around so much, the place that we will eventually settle in is probably something like this. So you can kind of think of it as like, we have some really jagged, but it may be some points that's slightly lower, and we may have some points, goes up again. We will probably end up somewhere here. Instead of using much lower learning rates, we may end up something, maybe here, right? Because we're jumping around so much. So now we're in generally the right area. We start to basically say, okay, let's stop jumping around so much. Let's decrease the learning rates and start basically finding, the good local minimum, but on a much smaller scale. So we're still doing that. We're jumping around, but we're jumping around much less because we know we're in a generally good location. And we do that 2 to 3 more times. And by doing so, we're able to find a generally pretty good local minimum. Does that make sense? Okay, cool.
So more like an empirical result.
It is absolutely more of an empirical result that they found that this works. So like, this is kind of how I'm trying to make sense of this. Maybe this was the motivation of why they did this, but then again, like people back in the days, they like at this point they had enough GPUs, enough computational power to just try out a bunch of stuff, and maybe they just found that this worked really well.
Also, it's much easier to get like lower to your minimum if you have a higher learning rate, but then after a while you just decrease it.
Yeah.
So you're kind of like controlling the learning rate as well from not like overshooting it. Like just kind of having a balance.
Yep. And right before we head into the break, I guess I just want to again remind you, like we couldn't have done this without batch normalization. And again, batch normalization and kind of variants of it, people call it group normalization and whatnot, is something that's used very prevalently today.
So just one question. Like, why would we have not been able to do this? Like, without a batch norm? Just like a
little recap.
Yeah, recap. Yeah.
Yes.
Because of the constraints of floating point representation, eventually you're just going to run out of representable bits
infinity. Right. Great explosion. That's exactly why. And I'll give another question that is a little bit more mathematical, but it will make sense in a bit. Here we're normalizing everything by the batch, right? So it's kind of just this one dimension. Why don't we just normalize everything? Why don't we take the entire batch of the outputs or take the entire feature map of outputs and just say, let's normalize that? Why is that the case?
Can you repeat the question?
Okay, so basically with batch normalization, we're normalizing across a batch, right? But why don't we just normalize everything? Like just take all the inputs and just normalize it. Why don't we do that? So the idea is this, right? When we're doing batch normalization, we're dealing with, this is a bit more mathematical, but we're dealing with a 1D vector, right? We're dealing with a 1D vector that is relatively kind of linearly separate from itself because each batch is kind of independent. With batch norm, it's not really as independent anymore, but we kind of treat it as independent. So we basically have one variance that we can calculate really easily with, if you have taken this probability course, we basically calculate the mean, and using the mean and then the square of the mean, we're able to calculate the variance. However, with a 2D input, with something like a feature map, what we will need is actually a variance matrix, because we will then start to need variance of every single pixel with respect to every single other pixel, because they are related to each other. They're not independent anymore. And because we have this, variance matrix, it becomes very, very computationally expensive to do normalization. So the reason why they settle with doing it just on the batch dimension is actually because, mathematically speaking, it's way too expensive to do it any otherwise. And nowadays people have figured out better ways of doing this called group norm, which is instead of doing the whole batch, you do like chunks of your entire output feature map. And people have figured out ways to do it quite efficiently. But back in the days, the reason why they did the batch is because otherwise it's too expensive. Does that make sense? Okay.
And wouldn't it also like simplify your distribution a lot if you did it for like the whole, you know?
Yeah, it would simplify distribution quite a bit because suddenly the features are kind of like competing with each other of being bigger, and
everything's like a normal distribution.
Yeah, and everything just kind of becomes a normal distribution. This allows you to kind of retain the uniqueness of every single one of the features, but at the same time, make sure that nothing is exploding. And yeah, before we continue, let's have a quick break. And afterwards, we have a little small Kahoot. And we will be moving on to some slightly more modern architectures of how residual networks and convolutional networks are used today. So yeah, let's have a 5-minute break. It's 10. Okay. And what I'm going to do is they can leave after, because we don't have that much left. We want to do a
I mean, we still have to keep this. Or I mean, can't skip the Kahoot.
Yeah, and let's do a quick Kahoot. And first of all, let me pause recording. Okay, welcome back from the break. Kahoot didn't work, so we're just gonna truck on with our workshop. Apologize for that. But now we're going to be talking a little bit about computer vision problem spaces. Basically, what computer vision is, what problems currently exist in computer vision, and how convolution neural networks are actually used in those places.
Yeah, sure. So basically, first off, what we've been talking about like for a long time now, classification. So like, is this a dog or cat or, you know, another type of animal or anything in general. So like it could be a vehicle as well. And the other two problems that we haven't really focused on are detection. Basically in like a huge environment, where is a certain like, I don't know, thing like where is the dog in this environment, and the CNN labels it for you. So this is kind of like, if you've heard of YOLO, you only look once. It's like a model that does this, just as an example.
Yeah. And fun fact, even though after 2017, the results of the ImageNet competition winners have gotten so good, they basically canceled ImageNet, or they stopped ImageNet. Now ImageNet lives on Kaggle actually as a localization challenge, where the goal is no longer to say, oh, what is this? It is to say, what is this? Plus, what is the bounding box of where this this thing is in the picture?
Right. Yeah, so that's why there's like a bounding box, and it can be applied in different problems as well, like in videos as well, like where a person's face might be moving or a ball might be moving as well. And for segmentation, I'll move out of the way a bit, but like it basically is what it means. Like it segments the image into different parts and labels it based on, you know, what it is. Here it's a not dog or dog, but maybe we could have like a different label for this, like depicting environment. Okay, so what's the difference between, so like there's two types of segmentation, first of all. One's regular and the other one is regular semantic and the other one's instance. So this one's more about like a pixel level, whereas this one is multiple instances of a similar class. So basically the difference would be basically that, let's say you have different types of things, although these look very similar. If you identify closely enough, you can see that this is like puffin 1, puffin 2, or puffin 3. So like based on the same class, like basically all puffins, which puffins are different. Whereas this is just identifying puffins. So that's kind of like the higher level of difference. And also you might be wondering, how do we like kind of just evaluate models for segmentation, right? So like we have classification, evaluation metrics like cross entropy loss, and you know, just kind of seeing like if it's in a class or not. So I guess something similar, but still sort of different that we talk about is we talk about something called, so like what are these predictions and what do these labels look like? So that's our like first question that we kind of like inspire ourselves off of. So basically, in the segmentation, like which parts should be which labels, and how do we like actually incorporate to check if this model is performing well? That's something called an adjusted randomized index, or AQI. So yeah, you want to go?
Yeah, I'll continue. So basically, what this leads to is something called UNet, and the UNet is basically it adapts the ResNet architecture, sort of. It uses a lot of the heuristics from the residual network, and it basically says, okay, how can we apply this to image segmentation? Because image segmentation back in the days is not nearly as much of like a hot topic. It was a very hot topic in one field, the medical field. Because if you're given some sort of medical imaging thing, you want to be able to basically figure out this part's a tumor, this part's not a tumor, or something like that. I'm not a bio major, but you know, something like that. Basically, that's what UNet was tested on. It basically completely wiped the floor of the competition with accuracy. And when I say wiped the floor, I mean like it went from 40% to 80% accuracy type deal. It did extremely well compared to previous kind of a lot more primitive methods, because this at the time at least was not a field that a lot of people was working on. Computational biology and medical imaging really became a lot more popular since deep learning have proved itself to be very useful. And UNet was actually one of the biggest pusher of it. So this is what the architecture of the UNet looks like. As you can see, it's called a UNet because it looks like a U. And basically what it does is it does this. You have some sort of input image, 570 by, you know, of some resolution. You pass it through some number of convolutional blocks, and just to kind of be very clear, every single one of these convolutional blocks, like after these, you will have like some sort of skip layer, right? So imagine kind of like skip layer happening here. And after that, you downsample. You do that a few times until you get to some sort of middle layer. In this middle layer, nowadays people have done some fancier things here, but basically in this middle layer, you have a few maybe convolutions, maybe fully connected layers, depending on how you implement it. And then you do something called up convolution. And basically what that does is this, right? If you think about what convolution is doing, when we have a convolution with stride, so let's say we have an image of like let's say a 4x4 image. Right? We have a convolution with stride. Let's say you have a 2x2 convolution with 2x2 strides. They may do something like you take these four, right? You do some sort of filter, sum them together. That's your first output pixel. And then you will go by a stride of 2, sum these together, and that will be your output pixel. So you can kind of imagine, you know, this block corresponds to here, and this block corresponds to here, right? So that is kind of what your normal down sampling convolution is like. Now, the up convolution, or what some people call transpose convolution, does the opposite. If you have a 2x2 filter here, what you'll do is you'll take that 2x2 filter, put it on top of this, and basically just say, okay, for this, for every single one of the entries, we do a pairwise multiplication, but we don't add it together. We let me see. Yes. So you put it on here, but we don't add it together. We just take the results and we just put it on, right? We take the kind of pairwise multiply results and we kind of just put it out there, and we just keep doing that. And because we're moving, let's say, just by a distance of 1, but we are using a filter of size that is bigger than 1, we're effectively upsampling the image. So we're almost doing like a fancier version of like linear interpolation. You can think of it that way. So that is, you know, in the highest level heuristics, what the up convolution is doing. And basically it allows you to, yes. Next slide. Yeah. Do we talk about it in the next slides? I think. Yeah. Oh yeah, transpose. Yeah, there we go. Yes. So transpose convolutions use it to upscale the latent space. So like, here's an example that we were talking about. So again, we have the inputs, we have kind of 4 separate kernels. And by using these kind of 4 separate kernels, we can basically kind of almost like superimpose them together. and create a higher resolution image. Right, so it is almost like learned upsampling, just kind of how normal convolutions are learned downsampling. So instead of doing a dot product, we're really just doing a pairwise multiplication, and sometimes we'll be adding things together. But that's what a transpose convolution does. That allows us to basically upsample images at a much higher quality than if we were to just blow it up, right? So that is kind of what this is doing. So how does this work intuitively then? And again, like these arrows are basically, you take the output of this, kind of just take a center crop, and you just kind of basically there's a huge skip connection where you concatenate it to the bottom here. So you're kind of retaining information across very long models. Like this is very deep, but we can retain a bunch of information across here to be able to basically say we can retain a bunch of information. And that basically smoothes our loss landscape and gives us a lot of benefits of residual networks. And if you think about like the particular task of segmentation, the reason why the intuition behind why we do this is this. We have very high dimensional data here, right? We have a very big image, and then we do a bunch of convolutions a bunch of times, and we compress it to a very small amount. This is very small, right? And then what we are basically trying to do is to go up to it and reconstruct information that is specific to the spatial feature of this image. By doing so, in this very small section here, what we're basically doing is we're learning the most important features of the image. We're kind of basically saying, let's not like memorize every specific pixel, but instead we are trying to capture the most important elements of the image and almost discarding the information that's not as important. And obviously in this case, information is a very abstract term because it's just something that only the model understands what to do with it. But that's basically what's happening, because we're kind of taking a lot of information, compressing it, or almost bottlenecking it, and saying with this very small amount of information, we must be able to, in the case of like another different network called autoencoders, be able to reconstruct the image or be able to get information about the original spatial, ideas of the image. And because in this very particular task, we're doing segmentation, what happens is with this skip connection, what we're doing is what intuitively is happening is this. This basically captures what each area means. And then by having these skip connections, we're providing the model with the information of the original image. Right, we're providing the model with the information of the original image, so the model is able to take the information of the original image / feature map at that point, and then the extracted information that maybe has a lot more to do with the actual segmentation itself, combine that together because we concatenate it, and via these convolutions and these up convolutions is able to come up with a segmentation map that ultimately works very well.
Is it kind of like similar to adding the identity where we discussed like?
Yes, it is actually exactly the same. Like what they're doing here is actually just saying, all right, because of the dimensionality, the output image is actually the output feature maps are actually slightly smaller than the input ones. More recent uses of UNets actually don't do that. If you're doing just like reconstructions of images, I'll talk actually. Fun fact: if you think about like have you heard of the term stable diffusion or like DALL-E, AI art, stuff like that? A lot of how they generate images, they actually use this network or variations of this network, where in that case, both the input and output dimensions will be the same. But like in this case, because the output is slightly smaller, they basically do like a center crop of it and then kind of just send it over there. Does it make sense, like intuitively, what the UNet is doing? Okay.
I'm just curious about like the segmentation, because we're compressing like the inputs into a very small dimension because we want to preserve the most essential information.
Yes.
So will that be a problem in the case where the object we're trying to the object we're trying to detect from the background is like occupies the majority of the image, and will like when we downsample the input to a very small dimension, will it be the case that we don't have enough pixels to store the information about the object we actually want to detect and segment from that image?
Right. So you're basically saying like the original object was, because it's very big, it contains a lot of information, but when we downsample and we compress all this down, it may not be that much. So that is where these skip connections come in. because we're providing information about the original image itself. So like, again, this is very hand wavy because like, we don't really know what the model is doing. But then like these layers can be almost focused on just capturing like what's different feature maps mean and vaguely where it corresponds spatially. And by then using information from the original image, it is able to say, okay, it's here. So
yeah. So just going off on that, like a lot of research, like a good amount of research in ML, like you create a network and you kind of intuitively create it, but it's more like a post facto explanation about why it works. Like after it like sort of works, you kind of reason why it works. And like the downsampling would capture like the most important features, even though if it like occupied most of the space. And like he said, the skip connections do provide most of the, basically most if not all of the information of the original. So
yeah. Any questions on the UNets? Okay, cool. Just before we end on the UNet, because like UNet is another one of those, 2015 was a good year for machine learning, but UNet is another one of those like extremely commonly cited papers, because nowadays with things like AIR generation and like generative imagery and stuff like that, a very big part of their backbone is actually using the UNets, or at least the second half of the UNet, but they're generating, they have some sort of feature vector that represents some semantic information about the image. Like that's actually how DALL-E 2 works and Stable Diffusion works. And then they basically use a bunch of convolutions to reconstruct the image, right? And then with the original diffusion paper, where they're generating image from pure noise, what they were basically trying to do is almost like denoising the image. They give it a noisy image, and they're basically trying to reconstruct the original image. It's more complicated than that, but that's kind of the general intuition. And basically what they do, they use the UNets, right? UNet with the bit of extra stuff in the middle called attention and transformers. We will talk a little bit more about that next time. But this is the architecture they use. And by doing this, they were basically able to say, okay, when we have a really noisy image, when we do this sort of downsampling, we're kind of saying, all right, let's focus on the most important features of the image. And because we're trying to capture the most important information, the noise is not captured. So when we reconstruct the image and we're basically trying to ask the model to denoise, it is able to learn how to extrapolate the most important features of the image and then reconstruct it, a denoised version of the image. And that's kind of sort of how AI image generation has gone about nowadays.
You can also sort of see this on Google. Like I've seen this in articles, but they have like this like pristine clear image and it goes to like kind of blurry.
Yeah.
Where it like learns the most important features.
Yeah.
And like they have like a noisy image and they construct it to the like.
Yeah, exactly. So you can kind of think of this as like hardcore bottlenecking, right? Because another thing that the bottleneck does that we didn't really talk about is because we're kind of restricting the learned feature map to be smaller than usual, we're kind of saying, all right, don't learn redundant information, learn the most important information. That's kind of that idea taken to the extreme. So yeah, okay, cool. Yeah, okay, one last fun thing that I want to talk about. We didn't actually talk about this last quarter, but I wanted to add it this time, which is randomly wired neural networks. So this was in 2019 when someone just, when she et al, they decided, why don't we just randomly generate neural networks completely randomly? Like every single one of these nodes you will see here are basically like kind of like a convolution layer. And what they were doing is basically you have like an input convolution layer and you have like a bunch of these almost like random skip connections going on. And they realized that you can achieve state-of-the-art accuracy with these randomly generated networks. In fact, this did better than ResNet. Empirically, it did better than ResNet. And I actually just want to say that this is almost like, in a way, this is kind of saying, does neural network architecture design actually matter? It still does a little bit, but then it's also a demonstration of how powerful ResNets are, specifically residual connections are, because you kind of think of these as like residual connections on steroids, right? Because of how many kind of skip connections are going on. In fact, like one of the papers that came out after ResNet, I think before this, is called DenseNet, which is basically, you can imagine normal residual layers being like, a bunch of layers like that. It kind of just does like this and that and like that. Right, you have your skips. What that step basically says is, all right, let's just skip all of them. Let's just keep skipping, right? Let's just skip every single possible combination, and they realize that perform better. So, yeah, that's a kind of my way of reiterating that residual connections are very powerful, and there's a reason why everyone's using it nowadays. Okay, so Bit of the miscellaneous topics, but let's begin with transfer learning. Actually, we're just talking about this just now, so that's perfect. We think we'll talk about it?
Yeah, sure. So I think Jordan brought this up before, but we're basically training a model that was like, used for like a different task, but for like our own set of like unique data. And basically, we think it would like perform well with some tweaks. So just kind of, this is what I said, but one example would be something like, this is actually from the neural networks class here, but like MRI scans and, CFAR10. So CFAR10 does like a model running on CFAR10, maybe like a ResNet, would do really well on classifying images. Whereas we can use that same like neural network with some tweaks to then like train on MRI scans and identify different things about them. So that's kind of where it is. Although we're not going to talk a lot about it, it's very useful because we can't always like create like novel neural networks for everything, and it takes so much time to train. So yeah. And these are like other methods of transfer learning, like freezing layers, like what ResNet is. And maybe like retraining and fine tuning. Although we're not going to go too deep into it, like it's probably good to take a look after.
Okay, cool. So let's talk a little bit about ethics. We are running late, so I'm going to kind of speed through this. But basically, machine learning is not that great for the environment because it takes a lot of heat and energy to train on CPUs, right? But one thing is you can actually use AI to actually monitor changes on the environments. A lot of like geospatial information and data is out there, and we can actually use machine learning to analyze a lot of that. However, if training a single AI system can emit over 250,000 pounds of CO2, someone out there has done like a rank, like, first of all, like train, like you're basically just asking a bunch of GPUs running really, really hot to both use up energy, but also you have to have some way of dissipating that heat. It takes a lot of energy in fans, or if you're talking about server rooms, huge cooling systems. That is kind of detrimental for the environment. And that's also why people were saying how crypto was really bad for the environment, is because it's kind of the same process of you just constantly maxing out the GPU. For example, Google's AlphaGo Zero, which is basically AlphaGo, aka AI that's able to play chess, but it's able to play chess just knowing the rules of chess and not having seen any human data. It's very cool. It generated 96 tons of CO2 over the span of 40 days as it was being trained. That's a lot. So that's kind of something to keep in mind whenever we're training AI models. That is why a big part of AI research is actually how can we design smaller models that perform equally as well, or even maybe just like slightly worse. And because designing smaller models also has an implication of you're able to put on phones and mobile devices and stuff like that. Okay, so this last section, you're free to go now, by the way. This last section is where I talk a little bit about Python and why we use Python, because I think it is a very interesting topic of how Python has became the de facto machine learning language. So if you think you're very familiar with Python package management, you can leave, but I'm going to try to speed run through this. Okay, so first, let's ask the question of what is Python, right? Like seriously, think about it. What is Python? Can anyone answer that question? Like just throw anything out. It's a programming language, sort of. But like, and I guess the better question is, another question is like, why is Python so popular for machine learning?
For machine learning?
Yeah, for machine learning. It's basically like the de facto language at this point. Now, if you're deploying machine learning models, sometimes you will use C++ if you're trying to do it very, very efficiently. But a lot of times the top end, like we're training things, is still Python.
You can just
take
a guess, yeah.
Because of the libraries that are available.
It's because the libraries are available. That's one of the reasons.
Because it's open source, yeah.
It's open source. A lot of libraries are available. And there's a second reason that I'll very quickly get into. And the second reason is related to the first question, is Python is not a programming language. If you have, who here has taken CS35L? Yes, you will know this because Python is a scripting language. And that is one of the two main reasons why we use it for scientific computing and machine learning. So A programming like programming language like C++ is compiled, aka it runs an executable predetermined sort of set of instructions. You write code, the compiler takes the code and says, all right, let's convert that to zeros and ones of a bunch of machine code that will be executed. That means the code runs really fast, right? Because the programmer knows exactly what it's going to do, but it lacks flexibility. And you'll see why in a bit. A scripting language is what we call interpreted. What is basically, we have a separate program, in this case, python.exe if you're on Windows, or just Python if you're on Macs. A separate program that interprets the scripts in real time, sort of. There's another thing called just in time, which is a different thing, but it is something that interprets the scripts and translate this text to something that it executes. And the key is this: python.exe does not have to stop running after it has ran all your code. So you type in a bunch of code. It doesn't have to stop running after it has ran all your code. It can just pause and wait for your next instructions. And that's the key idea here, because we can use something called Python notebooks. You can build a program as it is running, right? This is specific to Python notebooks, by the way. If you're just doing .python scripting, normally it automatically stops after a while. But that is why we may use something called Colab, because it is like a cloud implementation of this. So for example, we can do something like, we can set things to variables. And what we can do is, we set things to, A and B, 3 plus 2, it does the calculation. And then we can then go ahead, change those values, run this again, and it will give us different values, right? So basically, you're able to do stuff like this. And you can imagine how this will be very, very helpful for machine learning when, trial and error is, a big part of what we do. And you may not want to rerun the entire, let's say, the training phase again, and you're just testing out, different things that your model can do. That's how notebooks can be very helpful. And the second question is, why is Python so popular, right? And the key here, as you have said, which is packages. So the idea is this: Python has one of the widest selections for packages for math, machine learning, statistics, data science, scripting, APIs, and a bunch of quality of life improvements code. You know what, right? PyTorch is the machine learning library we use, but there's also things like TensorFlow. NumPy is kind of like our good old linear algebra library. Scikit-learn is kind of like a blend of the two. It was kind of the OG machine learning library with like not deep learning, but like if you think like KNNs and random forests and stuff like that, it's Scikit-learn. And also like, for example, Wikipedia has an API in Python, stuff like that. And the best thing is packages can be very easily installed in your terminal with pip install, right? So you can just pip install a package, for example, pip install NumPy, and you will have the package, right? So you can kind of think of the thing that what it's actually doing as basically with pip install, it just kind of searches in some sort of official repository. And when it finds the package it wants, it basically downloads it and it installs it to your computer. And the way it installs it is Python, they have something called an environment, which is, if you don't know what system variable environments are, it's basically a path that basically tells the operating system to go, okay, whenever Python.exe is ran on some sort of Python scripts, and the script says import blank, this is where you look to find that package. And then inside that directory will be where all your packages are stored. To manage these packages, you will want to manage them in something called virtual environments. Does anyone know what virtual environments are? Yes.
So when you install NumPy in a virtual environment, your original environment doesn't have it, something like that.
Yes. The original environment stays unchanged, and you're able to create multiple copies of environments, depending on which purpose. This is kind of like the analogy that I like to use, the Python kitchen, right? So with default Python, you have a bunch of built-in functions that you can just run without needing to import anything. So you can kind of think of these as like tools that are fundamental to your kitchen/Python environment, like your print statements, your open a file statements, your declaring a list, your iterator statements that allows you to do really fun things with lists and stuff like that, right? Like you can kind of think of them as the most essential parts of your kitchen. And then we go one level up, which are built-in libraries. These are tools that you always have in your pantry/imports. You don't have to install anything, right? But these are just things that things that are so commonly used and so also in a way so small enough and that you're able to just kind of have in your Python kitchen, aka your Python environment at all times. For example, math, obviously, that it does things like square roots and a bunch of more specific math things. Statistics, random, and OS, which allows you to like modify OS files, call shell commands and things like that. And the reason why they're kept in built-in libraries instead of just the default thing itself is, despite the fact that you use it a lot, it is not something that you use every time. There's usually for two reasons. Is first of all, it's not as commonly used and as integral to Python as kind of like your built-in functions. And the second thing is they're usually much bigger. They're much bulkier. So if you were to run Python with all those packages imported, but you are not really using them, what happens is when Python's executing, it is actually, when it's referring to function definitions, you have a lot more functions and libraries are being loaded. If you're wondering how these libraries work, they're also just like a bunch of .py files, where when you import .py files, it basically exposes these functions to be available to use. You can just call functions and classes from these libraries. And because you're doing that, you can imagine how then Python is becoming bulkier, right? Because it is looking through a lot more things and is executing with a lot more code that's being exposed to it than if you were to not import anything. The third level is installed libraries. These are the tools you get at the grocery store or by doing pip install, right? So basically, these are specialty tools that you only use once in a while. It is specific to every dish you make, aka it is specific to every single program / script / experiment you run in Python. These include things like scikit-learn, NumPy, and Torch. And the reason why they're not just normally available is because some people will never need to use them for their entire time using Python, because we all use Python very differently. And if you imagine having every single library being installed by default, your Python installation will be over terabytes or even petabytes large. So that is why they're basically installable. It is something that you have to actually go to the grocery store to pick them out, aka use pip install to install. And they'll help you do things. They abstract away tools. They give you a bunch of different predetermined Python libraries and sometimes even APIs to C code that makes what you're doing a lot faster and allows you to do really nice things like, let's say, use the GPU to do machine learning. And this is where virtual environments come in. And this is where the analogy starts to break down a little bit. So basically, the idea of virtual environments is that you have, first of all, every time that you buy something from your grocery store, it becomes infinitely reusable. And the second thing is, whenever you want to, say, make a different dish or a different style of dish, you may want to duplicate your kitchen, start from scratch with just the built-in functions or in countertops and built-in libraries in your pantry, and not have the extraneous libraries you have installed. And the reason for doing so is because sometimes you may have things such as package conflicts, right? You may have version conflicts between packages. For example, PyTorch and TensorFlow, if you both want to use GPU for them, actually use conflicting versions of the NVIDIA API. I've experienced that firsthand. Don't install them in the same virtual environment. You will cry. So, for example, it is stuff like this that makes virtual environments so helpful, because you're able to kind of isolate environments to only include the packages that you need. Another thing about only including the packages that you need is when you send off your code to someone else and you say, okay, run my code, and they may need certain packages, because let's say in your environment, you only have packages that you need. You know exactly which packages they have to install so they can run your code. So that becomes very, very convenient. And this leads us to Google Colab, or kind of package managers, right? Basically, what package managers does is you may have actually multiple environments that, let's say, has PyTorch in it, right? And PyTorch on its own is like 2 gigabytes, right? If let's say you have 10 separate environments for machine learning, and each of them require PyTorch, but they have slightly different packages that conflict with each other, so let's say you have 10 of them. If you use normal virtual environments, what happens is you will install 10 copies of PyTorch. That's 20 gigabytes. However, if you're using the same version of PyTorch, what package manager, specifically what Conda can do, is you just have to install PyTorch once. It will kind of cache it in this kind of list of mega list of libraries. And every single one of the subsequent virtual environments you create are basically almost symbolic links that points to that library. So you're almost reducing redundancy by actually using virtual environments. You're able to kind of pick and choose the packages that you only want to include within every single one of your virtual environments without creating redundancy. Yes.
If we're not using conda, we're installing over and over.
If you use like VENV, you have used that. If some of you use it before pip, they have like built-in VENV, you will be installing things over and over. Yeah, that is why for VNV, it asks you to create like a VNV directory. That's where even including your Python version is stored, and everything is stored in there. Your patches, everything. So you're actually installing things over and over again. It's really nice if you want a completely clean environment to make sure nothing is relying on anything else. But if you're just doing a bunch of machine learning experiments and you need a bunch of different environments, for example, with machine learning classes, I usually create a different environment for every class I'm doing, then conda is very helpful because it reduces that redundancy. It also makes it so that when you create a new environment and reinstall things, you don't have to wait for it to download. It just kind of caches it for you, which is really nice. And this is where Google Colab comes in. Python gives you a lot of flexibility. And because of that, we can actually use Google Colab for Python notebooks. And the reason is a lot of machine learning packages are pre-installed for us. PyTorch is there, scikit-learn is there, everything, a lot of things are there. And if you don't have that thing, you can also just install it in Colab. It's the exclamation mark that allows you to run, shell commands. You can do like exclamation mark, pick and install the package that you want. And because of that, we also don't have to worry about package management nearly as much because Google has sorted out the conflicts between TensorFlow and PyTorch and the conflicts between packages for us because they're all installed there, which is really nice. And another thing is Colab also sorts out some other problems like, version conflicts, GPU compatibility for those of you who have slightly stranger / newer GPUs and you're trying to install drivers that PyTorch works with a GPU, you don't really have to worry about it because you're using cloud GPUs and other really small things. So that is why we use Python. And that is why Python is really nice for machine learning. Obviously, it's not the only language with this feature, right? So the two factors is because it is a scripting language and it has so many packages. Because there's a lot of other scripting languages out there, MATLAB, R, but they don't have nearly as much sort of package support. And that is why Python is so popular. Anyways, thank you for coming today. Sorry for holding you guys for a bit long. We finally have a feedback form. And next time, we're going to be talking a little bit more about transfer learning, word embeddings, and recurrent neural networks, which is something that works with time series data and something very popular nowadays, which is natural language processing for stuff such as ChatGPT. Hope to see you next time.